So in the previous lecture, we learned about graded potentials and how those graded potentials in the cell body and the dendrites of a neuron will influence whether or not the minus 55 millivolts threshold is reached at the axon helix. And remember, as long as we have enough depolarization at that axon helix, we will trigger action potentials down the length of the axon. So the signal will be electrically propagated through the axon to the axon terminals. But if the depolarization is not substantial enough to reach minus 55 millivolts, let's just say there's one here, then no action potential happens, and therefore there's no electrical conduction of that signal. So what we're going to do now is take a look at the fact that it's rarely just one neuron synapse to another. Although you can find those examples in the peripheral nervous system and the central nervous system, a single cell body and its dendrites might actually have thousands of presynaptic cells synapsed to it. And so really, when you have multiple presynaptic cells all working on the same postsynaptic cell, the graded potentials are going to be summated. So this lecture is going to look at those summations. Now the first thing that we're going to do is we're going to look at what is called spatial summation. And spatial summation is the idea that I have here. We have multiple different presynaptic cells all synapsed on the same postsynaptic cell. And the overall graded potential that we get at the axon helix is going to be the addition or summation of the graded potentials that come from all of the different presynaptic neurons that are firing at that time. So I have actually two different colors here. I have red and I have blue, and I have those on purpose. When I think red, you kind of think warm or hot, and blue is like cold. So going back to a previous lecture on neurotransmitters, we also learned that certain graded potentials could be depolarizing and certain graded potentials could be hyperpolarizing. I mean, if you let chloride through, that's actually hyperpolarizing. So we are going to assume that any neuron that is in red here, and I'll just highlight a couple, are going to be paired with sodium channels in the postsynaptic cell, and therefore, if they fire, they're going to let in positive charge and depolarize the membrane. We call such presynaptic neurons excitatory neurons. Okay, so excitatory, we talked about that phrase, excitability. When you have high excitability, you're more likely to have an action potential. So excitatory neurons are going to be ones that make it more likely for the postsynaptic cell to have an action potential, or at least have enough depolarization to start an action potential. The converse are going to be presynaptic neurons that are paired with chloride channels. And when they open, chloride comes in and hyperpolarizes the membrane and actually takes that membrane potential and drops it and makes it harder for that postsynaptic cell to generate an action potential. So we call those neurons inhibitory neurons. And in my drawing, I have them colored in blue. Okay, so spatial summation refers to the idea that you have different neurons that are coming in at different spaces or in different spaces. and that if they are firing at the same time, the overall membrane potential that is seen in the axon helix is actually an addition of all of the localized graded potentials that are coming in from different spots. So let us assume for a moment that we actually have one excitatory and one inhibitory neuron firing at the same time. They kind of cancel each other out, right? So do you think that we're going to reach minus 55 threshold there? No. So in other words, the positive charge that's coming in is canceled out by the negative charge that's coming in. And so the membrane potential seen at the axon helix probably isn't going to be greater than minus 55. That's an example of spatial summation. So in this example here, we have 3 excitatory neurons that are all firing, which means they're all releasing their neurotransmitter at the same time. And so they're all causing depolarizations. And while one by itself might not be enough to reach the minus 55 millivolt threshold, all 3 of them, when they're added together, is enough to reach minus 55 millivolts threshold and therefore start action potentials. But when you swap out one of those excitatory neurons for an inhibitory neuron, you can see what happens. We still have a plus, and then the negative, but the plus and the negative cancel each other out, and that single plus isn't quite enough to reach minus 55 millivolts threshold, and therefore no action potential happens in the postsynaptic cell. So that's the idea of spatial summation. And again, in the central nervous system, you can have many, up to thousands even, of presynaptic cells all synapsing on a postsynaptic cell and attempting to kind of gain control of that postsynaptic cell. In this image here, hopefully you have a pretty good idea that this is going to be the cell body and dendrites. All those little white buttons, they almost look like those little white firecracker poppers that you can get in like a little box that you throw on the ground and they make little pops. Those are all axon terminals of presynaptic cells. The yellow ones, the yellow Hershey's Kisses that you see, are going to be glial cells, so don't worry about those. But you can just see how many there are. And the book also has a nice picture showing a single dendrite, and you can see the distribution of excitatory versus inhibitory neurons, where excitatory neurons are synapsed in the red spots, and inhibitory neurons are synapsed in the blue spots. So again, it's just another example to show that particularly in the central nervous system, there are lots of excitatory and lots of inhibitory neurons that are all synapsed on the same postsynaptic cell, trying to kind of gain control of it through either depolarization, which is trying to say, yes, send the signal, or hyperpolarization, which is saying, no, don't send any further signal. This signal is dead. Kind of an interesting idea. And moreover, when we think about different ways that we can modulate signals with inhibitory neurons, there's not a one-size-fits-all. In this example here, I'm actually going to focus on the bottom first. This one looks at an inhibitory neuron and an excitatory neuron that are both firing at the same time. So this is spatial summation. And because they are firing at the same time, they cancel each other out, and therefore no action potential happens, and therefore no neurotransmitter is secreted from any of the axon terminals, right? So any of the cells that are themselves synapsed to this particular neuron are not going to receive any signal. But consider if I take that inhibitory neuron and move it somewhere else. In this example here, it's actually moved to the axon terminal itself. Kind of interesting. So what's happening here? Well, now we have an excitatory neuron that is generating enough positive charge to start action potentials. The action potentials are going to separate down all of the axon terminals, and when they get here, we have neurotransmitter released, but look at what happens when the inhibitory neuron fires at the same time. the inhibitory neuron creates enough of a hyperpolarized environment that the action potentials are killed. And so no neurotransmitter is secreted. So inhibitory neurons usually act as modulators, where they try to prevent signals from happening, and it's a good thing. You might think inhibitory is a bad thing, but you don't want to act on every single piece of information that comes your way. And I'll just give you a very, very brief idea of what I mean. Right now, you hopefully have clothes on. Lots of clothes, right? So I've got lots of clothes. I've got rings, I've got earrings, I've got hair that's in my way. I've got lots of things touching my skin. That is all sensory information that's being picked up by sensory neurons that are then conveying that to my central nervous system. Now imagine if I was constantly aware of all of that pressure and acting on it. I'd be like, I can't function because I'm constantly addressing too much stimuli. So instead, I have inhibitory neurons that recognize the position of your socks right now, the fact that you're wearing rings, the position of your underwear, doesn't matter. It's not causing you any pain. It's not causing you any trauma, cell death, or problems. So therefore, we're going to inhibit it so your central nervous system is not processing that information, and it's not right up here in that frontal cortex going, must be something I deal with. So inhibitory neurons are actually a good thing. Our last type of summation is temporal summation, and that is going to be where a single neuron repeatedly fires onto another neuron. So you have one neuron that's just basically submitting neurotransmitter after neurotransmitter after neurotransmitter, and the signals can add on top of each other as long as those neurotransmitter firings or secretion are very, very close together. And so in this example here, it's showing you a single excitatory neuron that is firing twice, but kind of far apart. So it fires a neurotransmitter, and that brings in sodium to the postsynaptic cell, and you get this little blip here of depolarization, but it rapidly dissipates, and then you return to rest. And then the presynaptic neuron fires again, and you get a little blip here, and then we return to rest. But if that presynaptic neuron goes fire, fire, one right behind another, one secretion of neurotransmitters followed by another burst of neurotransmitter, then the first graded potential doesn't completely recover before the next graded potential happens, and they build on each other. And so now you can see that you've reached threshold. And once threshold is reached, then you start action potentials. So when we talk about summation, it's not always spatial. You can have single neurons that are really having an outsized effect because they're just going fire, 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 fire right on top of each other. And the localized depolarization or hyperpolarization never really has a chance to recover before an additional influx of ions happens and they build on each other. So that's temporal summation. Let me briefly write out the difference between spatial and temporal summation, and then we'll be about done with this lecture. All right, so there's my definition of spatial summation. And in blue, I have another way of thinking about spatial summation. Okay, so there's my description of temporal summation. The last thing I'm going to do is leave you again with this table of graded versus action potentials, because we now have the ability to look at more of this information. And so one of the things that you'll see here is that graded potentials, which again occur in the dendrites and cell body, can sum, whereas action potentials do not sum. And then strength of the signal can be summed. Action potentials cannot be summed. So that means they can't be added together. All right, so that concludes our lecture on the importance of graded potentials and how summation works. In our final lecture looking at graded potentials and action potentials, we're finally going to turn back to the relative refractory period and coding stimulus intensity for sensory neurons. So I'll see you then.